Okay, hello. Thanks for joining me for the live stream. If you're able to do that this week, I appreciate it. If you're watching the video later, then hopefully your week has been a good one and will continue to be a good one. So we have a project due at the end of the week. There's nothing new to learn for it. We had all the tools we needed for the second project 2 weeks ago, but we did have a question about that I didn't get to last week about how do I, for the file processing part, how do I deal with things like extra fields and blank lines. So I'll start with an example of that. Just hopefully that's the last thing that some of you need. Happy Monday, Edcast. Nice to see you here as always. Hope that your week has gotten off to a good start. Glad you could be here. Yeah, so we'll start with that, and then we will continue on with the new content stuff. So last week we started to, we introduced the syntax of pointers, and this week we are rolling into the next big thing, which is using dynamic memory and pointer syntax to build fancy data structures. The first data structure won't seem that fancy, but it's kind of the fundamental dynamic data structure. So we'll start with it, and then we will build a series of increasingly complex and kind of sophisticated data structures with our ability to manage memory manually in C++ and our ability to use pointer syntax to do all that stuff. Okay, so that's where we're at. Maybe what I should do is just go down on the home page. I don't know if this has happened to any of the rest of you, by the way, but Canvas for a few minutes this morning was acting funny for me, meaning it wouldn't load. It would load the gray bar on the side of the screen with the links to inbox and stuff, but it wouldn't load the pages for a little bit this morning. So I don't know what's going on with that. Fortunately, it's free. So, oh wait, it's not free. Never mind. So I will complain. No, not acceptable. Okay. So here we are, homepage, schedule, project is due on Sunday, August 30th. And notice that the next project comes up on us the Sunday before the week of Thanksgiving. So the labs will all be oriented toward helping you complete the third project. So the labs are important because as you are building out the labs, you are getting the building blocks and the algorithms that you need for the third project. So I know you need to polish off the second one, but the third one is starting to show itself in terms of what we're doing each week. Okay, so Edcast was also having Canvas issues, so at least it's not me, and nothing else was wrong other than Canvas. I guess that they're for an enterprising person out there. I think building a competitor to Canvas is still an option. um, anyway, not my favorite piece of software in the world. Where was that? Okay, yeah. So new content, linked list, which leads us toward the third project, which I know is kind of catching you at the end of the second project cycle. Just is what it is. I wanted to give you some extra time on the second project because of the file processing part, which is new to some people, but we couldn't let the time go spinning our wheels on old content. So here we are. Happy Monday, Magenta. Glad you're here. Okay, so that's where we're at. Let me walk through the module real quick. So we are building a thing, beginning to build a thing called a singly linked list. This week we will continue to use exceptions, and for short-term purposes at the very least, if you just kind of get in the habit of thinking that we're going to use exceptions to deal with bad pointer stuff, then that's perfectly acceptable, because that is what we're going to do, is use exceptions to deal with naughty pointer things. So short amount of reading, which is just kind of learning to conceptually what a linked list is, and then there's a reading to compare it with arrays, which hopefully everyone knows what an array is. But anyway, I'll talk about that a little bit after we do some file processing tips. Lab 10, which I will come back to. So this week's discussion is something that we've done before, which is, I think we've done it in your class. I know I have the PNA1 people do it a lot, which is to encourage you to go out and find other perspectives, other people trying to explain how linked lists work. There are some fun ones on YouTube where people try to kind of illustrate, either with like live human actors or with graphics, the way that linked lists work. But the idea for the discussion this week is simply to gather up as many different perspectives on the concept of a linked list as possible. Text, video, graphics, whatever it is, to give ourselves, each of us, the sort of maximum chance of coming to an understanding of them sooner than later. It's a different kind of thing. We're having to deal with the dynamic memory, we're having to deal with the pointer syntax, and then we're having to use those tools to develop a dynamically allocated linked data structure. And then the reminder, so lab and discussion as always, and then the second individual project, which I get the sense that some of you are probably already done with it and you are in the polishing phase, which is a great place to be. Yeah, the more of us that can be in that habit, the better, that we get down to the end of the project cycle and we long ago finished it, and now we're just kind of checking and double checking ourselves to make sure we got the requirements. And if you didn't see it, one of your classmates put a very useful question in Piazza this past week, just clarifying what the requirements are. So if you didn't see that in Piazza, please go read it. Which was a very nice thing that one of your classmates did, was to put that question out there for everybody to see and see the answer to. All right, let me go back to the project so that I can get back to it quickly when I want to. The lab, sorry. Before I leave that, I am going to go back to the project. So things to be careful of are the requirements. Now, I kind of write the instructions with a fair amount of detail. Your classmates, I went in and I made some what I think are simplifications to save you some pain, which is to be specific about what fields were going to be needed, although you could have figured that out for yourself, no doubt. So I didn't change the requirements, but I did add some language into the project when I was uploading the pictures into it, the screen captures of mine, to try to make it clear. But anyway, you want to read the instructions, of course. which have important details in them, and then also make sure that you review the rubric at the end, which I will use, of course, when I'm doing the scoring. Okay, so there's that. And then screen caps that I added a week ago or 2 weeks ago. I can't remember now. My implementation, so loading the file, the menu, an option has been selected. So now you're supposed to ask them, how big of a view do you want? I limit them to a maximum of 10 so that it fits nicely on the screen. Good morning, Tony. Nice to see you. So anyway, screen caps from my my own implementation of this project. So yeah, there's so please do review those things. You want to leave yourself time to do that. Review the requirements. Make sure that you are hitting on all those things before you call it done. You can resubmit projects, by the way, although in your case, submitting the link doesn't mean you can't go do updates in the REPL. I do try to turn out the grades pretty quickly, but anyway, before you call it done, make sure that you've reviewed the requirements and address them to the best of your ability. Okay, lab loaded. So let's go deal with the issue from the agenda of the extra file processing bits. So I'm not going to upload any of this because there's not anything complicated in here. Just so that you've seen it and get the idea. So this is 20 P2 tips file IO. Call it that. Okay, so let me make a file first. I'll just call it input.txt. And then I'll just do some things. So let's see, we'll call it, we'll have these labels at the top. So name, category, quantity, price, calories. Let's do an ID number in here too. So I'm just doing that line to kind of remind myself of what the fields are. And in fact, I'm going to change the field separator just for fun. So we can talk about that quickly as well. So I'm going to do just a quick example of parsing a file like this. I'm going to put a blank line in there on purpose. So just say apples, fruit. I don't know. We'll call it 1, 1, 2, 3. ID 1000. Say 3 apples. Price. I don't know. 0.75 calories. I don't know how much an apple has. I'm going to say 120. Do another blank line. In fact, let's do comment. So fruit, beverage. Oops. Oh yeah, coffee, which is the beverage category. I'll make that ID 2010. Doesn't really matter. Quantity, 1 bag of coffee. The price is going to be expensive, I think. And the calories is basically none. Tea, beverage. 2011, let's say half a dozen. I'm getting bored of this part. That's enough. And what the heck, another blank line and a comment, and we'll just say that what will come next is a snack category. So here's an input file, and it's got just a bunch of garbage in it. It's got this line at the top that kind of tells you, oops, dummy. How do you replace? I guess I'm just going to have to manually replace. Thank goodness I didn't do that many of them. I'm doing the different separator just so you see an example of it. What the separator is doesn't matter as long as it doesn't cause problems for the processing stuff. So one thing to note about separator characters, when you have a text file with data in it, you don't want the separator characters repeating themselves in the actual data. That causes huge amounts of problems. Our input file this week actually had some of that, so I went and I cleaned those out for you so that you wouldn't have to deal with them, and I took some other garbage out of it as well. So I have sanitized your input file for your project so that the separator character is never used anywhere other than strictly as a separator character. So in this case, the exclamation point is the separator character, and I need to choose a separator character if I were doing this that I assume is not going to appear in the middle of any of the actual data itself. So this first line is just telling me what are the fields. With these little labels, it tells me what the fields and the separator. And notice the hash symbol, which I'm using as a way to make a comment line in the file. That's something that I want to ignore in my processing. I have a blank line, which I want to ignore in my processing. It breaks stuff. I have another comment, which I want to ignore. Now I have an actual data line that I need to parse. Comment, blank line, ignore, comment, ignore, parse, parse, ignore, ignore, ignore. So how do we write code to do that? It's not hard. I'm not doing any of the usage stuff because I want to save myself the time and the trouble. And I'm using the global, the sort of catch-all using directive to save myself trouble. So I'm going to read. And I've hard-coded the file name. Don't do that for project 2. I believe, let me go look. Well, maybe I didn't ever say that. Yeah, I never said that. I wouldn't do it, but I guess I didn't say it. Technically, you're allowed to do it on the project, so I will strike that comment. Okay. A little sanity check, of course. I'll go ahead and put an output. Oh, it's hard-coded. Not the best. Okay, so anyway, here we are. We're ready to process the file. We opened it. We checked to make sure it's good. Now we grab a string and we start looping the file. So for starters, let's just put out all the lines and make sure that we get the file back intact. And an end of file marker so we're going to know when we got to the end. So this also I'm just suggesting to you, if you haven't done this part, you don't have to write every last little tiny bit all at once. You can just start with, can I even read the file and print its contents to the screen? The answer is yes, yes I can. So one thing I'll notice is that there's a blank line at the end of the file, which seems to not be picked up here. That's fine. It doesn't matter. I don't care about the blank lines anyway, because end of file happens butted right up against snack. But if I look at the input file, there's actually one more line down here. So it appears that this way of reading the file will just pass over a blank line if it's the last line of the file, and I'm good with that. Okay, so now how do we strip out the blank lines? Let's start by getting rid of the blank lines. Well, that's easy. Let's just ignore. So we'll only take an interest in lines whose size is greater than 0. So simple enough. That should ignore the blank lines. And now the blank lines are gone. What about the ones with the pound sign at the front? Well, I can just add logic for that. So if the line is greater than 0, potentially good, but also the first character should not be a pound sign. So I'm ignoring two kinds of lines. I'm ignoring blank lines. So in other words, I only want to keep the ones that have a size greater than 0. And I also only want to keep the ones that do not have that marker at the front of them, which are the comments. Okay, comments gone. All that's left is the data lines. Great. So now let's do some parsing. So let's say for this example that I have a struct food. And all I'm really interested in about food is the name of the food, the quantity of the food, and the price of the food. So there's fields in that file that I don't care about. I don't care about the category. I don't care about the ID number. And I don't care about the calories for my problem. So I don't have to change the file. I just... oh yes, Isnam, you are correct. So Islam asks, instead of the size being greater than 0, could I say the ones that are not empty? And I like your idea better, Islam. So let's go with yours. So instead of size greater than 0, let's just say the not empty ones. That reads better, I would argue. So great idea. I think that's an improvement because now the code reads more like what it's supposed to be, which is not empty ones. So yeah, I like it. Okay, so just to point out here, so for my application, I have this input file. It's got data in it that I don't care about. That's not a problem. I will just ignore the parts that I don't want. All right, so now we are, I need a... an S stream. Okay, so now we've ignored the empty ones. In fact, in other words, we're only looking at the not empty ones, and we're only looking at the ones that do not have the comment marker on them. Okay, so now let's do parsing of only the fields that we care about. It's helpful to have the input file labeled so we know that we want the first field, 2, 3, this third field, and the price field. So we're ignoring calories, we're ignoring ID, we're ignoring category for our little sample application. So how do you ignore fields? The easiest way to do it is like this. So let's see, we need an iStream stream parser, which will be built on that line. And we will, for our purposes, let's just say, let's also make a food here. So what I called it, food, yep. Okay, so make a temporary string, and then we'll start. So first field, name. So we will get line parser, parser, up to that thing. Something's wrong. Oh yeah, temp, up to that thing. So the first field, we want that, right? So f.name equals temp. Great. Second field, category. We're just going to chew it up. So we'll still get line on it. We'll still store it in temp. and then we will do nothing with it. Just, that's it. We just consume it. Third field is what? ID. We don't need the ID, so I'll just consume it. I don't need to translate. I don't need to convert it to an integer. I don't need to do anything because it's just going to consume it as a string and keep going. Fourth field is 1, 2, 3 quantity. So I'll go ahead and consume it. This one I do want. So this one we're going to say, we'll take our food instance dot quantity equals string to integer temp. Should be all right. So that one I'm not ignoring. Fifth field, price. This one I'm also interested in. So I'll go ahead and consume it, and then I will string to float it. And then what's left? Calories. I don't care about it at all. So since nothing follows it, there's no need for me to consume it to get to the next thing. So I'm done. I don't need to even do that work. That's fine. I'm done. So let's see if it worked. Just real quick. Food. F.name. Comma. F.quantity. Let's drop down. At. I didn't do any of the formatting, of course. F.price. We're just doing this as proof of concept. Okay, so there's the apples, correct? There's the coffee, and there is the tea. Did I make the tea? Yeah, I did make it 375, and then we're at the end of the file. So that's that whole problem. How do you skip fields? How do you skip lines, empty ones, and comment ones, which is kind of the logic is reverse here, of course, where I want the line, if it's not empty, I want to try it. And also that it's not a comment, then I want it. So there you go. There's that whole part of the problem. Yeah. So I'll stop there for a moment and just see if there's any questions come up. This sample, I don't think there's any need to share it because it doesn't do anything particularly interesting. Kind of all the ideas are right here on this screen already. Okay. And that I've shown the input file several times, but I'll switch back one more time, leave it there for a few seconds. That was the input file that I did as an example to show comment lines that have the pound sign at the front, blank lines so that we could demonstrate how to ignore the blank lines, and then the data lines. And then I also used a different separator character just to show you that, that it's trivial to parse with a different separator character. Just change the get line calls. So there's the input file, and then here is the bulk of the processing. But anyway, that was a question from last week that I had to roll over because I went 2 hours last week and thought I needed to stop. All right, so hopefully that's helpful for finishing off the second project. This is actually one of the easier parts of the second project. There aren't any super difficult parts of the second project. For me, most of the work on my implementation for project 2 was in the user interface, the menus and getting the format worked out, which I had to stretch out my terminal to get things to look nice, which you are free to do if you want to. And then some loops and some sorts. I will show you one more hint on the project. C++.com. So our second project is going to have vectors in it. So let me just show you some hints about vector that you are going to use. The two big ones, anyway. Actually, the one big one. Where'd it go? Or maybe it's not listed here. Reserve, shrink to fit. Somewhere else. Let me go look it up separately. So, well, I'll just remind you this way. We need this standard sort. We did a lab with this, so you have experience doing this. We did a sort on a vector full of structs. We had to write comparison functions to make that work. So we did a lab, and we're just repeating that same work more times on the second project. The other thing that can be super, super, super handy is this reverse. And it has an example of usage in here. So one way to deal with how do I do a descending versus an ascending sort. So if I assume, for example, that the ascending sort is the default, the way to get descending sort is simply to sort and then reverse immediately after the sort, and now you have it flipped over. So I used standard reverse in my implementation. There's other ways to do this. You could simply write a loop that iterates from the back to the front. But I used reverse to just make the code simpler for myself. And it has a usage example, so you can see how that would go. Okay, that is it for project 2 stuff. Let's move on to new things here, which is linked lists. So we have to switch our brains over to a different problem, and hopefully to help you do that, I'm going to draw pictures and then sort of translate the pictures into code. So I suspect if you ask most people who have been through a computer science curriculum, I could be wrong, but I think this is probably true. Most of us became a lot more confident in terms of our understanding of these dynamic data structures once we could draw pictures of things. Drawing pictures to help you work out the bugs in an algorithm, drawing pictures to help you understand conceptually how these data structures are put together is very, very, very useful skills. So, okay, so Tony agrees with the usefulness of drawing pictures. It takes practice. So the time to start would be sooner than later. So anyway, I'm just showing you as the way I understand these by drawing pictures of them. So let's start with a view of arrays, vectors, and then the linked list on top of that. So if you think of an array, and it has data elements in it, right? I'll label it. This is an array. So the things that we know about how arrays work, they are of a fixed size. In this case, the fixed size is 4 elements. um, access by index which in C++ always starts at 0. So sorry about this shadow. Hopefully it's not too much of a distraction. So we access the individual elements by index, right? And C++ uses zero-based indexing, which is what most languages do, but not all languages. It's very off-putting to me when I encounter a language that does one-based indexing, because it doesn't make sense in terms of how it actually works. Because what an array really is a memory location and then offsets from that memory location, which if you are taking or will take the assembly language course someday, this will make more sense to you. But anyway, C++ uses zero-based indexing, which is why we have this kind of syntax when we want to access individual elements. One of the nice things about these index addressing on arrays is that it's fast. If I say index 1, the computer can literally just go straight there. There's no kind of work to get there from either end. It just goes there. So arrays are fast for this reason, because the direct indexing means that I can very quickly get to the element that I want and very quickly CRUD it, right? I can very quickly overwrite the data there. I can very quickly read the data there. I can very quickly update the data there. Technically, I can't delete the data, but I could overwrite the element with some marker that says that this is an unused cell. Either way, they're fast. But they are somewhat inflexible because of their fixed size. So this array, as an example, as long as I only have 4 elements, life is good. If I get a 5th element, I'm in trouble because the array can't flex around that new element. All right, so there's the array. And I'm going to wad it up and throw it on the floor because that's going to feel good. All right, vector. Vector. So what's cool about a vector? Can grow and shrink, but not efficiently. So vectors are awesome because they can grow and shrink, but the catch is that they don't grow and shrink very efficiently, meaning they consume computer resources when they grow or shrink that they needn't necessarily consume, but that's how they work. Basically, a vector is a dynamic array, and every time it needs to accommodate more elements, it has to allocate a new, bigger array, copy the elements from the old version into the new version, and now you have the new, bigger array. So there's a lot of work for the computer to actually pull off a vector. Every time it grows, a new array has to be created. Right, so if I need to add another element to my vector, then I literally have to grow it by 1 and then copy the old elements down into it. So it can grow and shrink, but it's not efficient to do that. So this is the downside to the vector, is it is an inefficient way of doing dynamic memory. It just happens to be very handy. It does have direct access by index. and it's zero based as well. So that's a good thing. So it's flexible but not super efficient. And the reason I talk about this briefly is because um, there are more efficient ways of having a dynamic collection than what vectors do. Vectors are convenient. They are mostly like arrays in terms of coding them, so they're easy to code. Um, you can avail yourself of a lot of the sort of standard library algorithms, such as sort and reverse. So there's a lot of good things about vectors, but they give up efficiency for being flexible while still allowing you to use the array style syntax on them. So things to consider. Vectors are not at their best when you have a lot of data coming in and going out constantly. They're not efficient because you have these sort of bigger, smaller, bigger, smaller, bigger, smaller, and all these copies have to be done in the meantime. Okay, so where we're at now then is creating a dynamic data structure that is better at the efficiency part in some ways, at least. We'll start with a singly linked list, which have a lot of applications, actually. Stacks and queues can use them nicely. Anyway, we'll worry about that later. Singly linked lists. So what we are doing is looking at a variety of different data structures in this class, each of them with its sort of good parts and bad parts. So arrays are great because they're fast and efficient, but they're inflexible. So if you get more data than your array has been created to store, you're out of luck. Vectors take care of the problem of arrays being a fixed size because vectors are basically dynamic arrays. The trade-off with a vector is that dynamic behavior is inefficient when it comes to using the computer's processor and memory resources, because every time you have to grow a vector, you actually have to create a brand new, bigger array, copy the old array into the new array, and then get rid of the old array. There's a lot of work involved in a dynamic, in a vector. So where singly linked lists improve upon that is that they only ever use as much space as is required to store the data that it is storing, and that's it. Whenever you grow, you don't have to grow the whole structure and do any copying of things. Whenever they shrink, you don't have to create a new structure and copy the things. So singly linked lists are very efficient in terms of the amount of memory they use for the data that they store. They are less efficient at accessing random things in the middle of the list. So arrays and vectors are way better when you need to sort of quickly get at things in the middle of the collection. That's better for arrays and vectors. Where singly linked lists are better is in terms of never burning more memory resources than they actually need for the data that they have. The downside for us programmers is that singly linked lists are more complicated to create and work with until you get used to them, at least. Okay, so there we have it. So what is a singly linked list? Let's start with the building block of a singly linked list, which we call a node. So when we think of an array or a vector, we think of the entire collection all at one time, kind of like a shopping basket. A singly linked list is a lot more like a chain. And every link in the chain is a new piece of data. And we only have as many links in the chain as there are pieces of data to store in it. So that's one way to conceive of how a linked list works. It's not the whole shopping basket. It's actually each item kind of linked together with the next item. There's an item. There's another item linked to it. I can't do that in the camera. There, kind of, right? I don't know if you remember, probably most of you don't. There was this thing called Hands Across America, where the people tried to make a human chain of people holding hands and stretching it as far across America as they could, which is probably in the 1980s or something. But anyway, Hands Across America is like a singly linked list in a sense, because you have a person and then another person walks up and grabs their hand, and then another person walks up to the end, grabs a hand, and then another person, and the chain or the list of people keeps growing. So Tony remembers Hands Across America. Cool. So that's helpful, at least for you. So anyway, Hands Across America, where you have this sort of chain of humans linking themselves together by holding hands, is a lot like a singly linked list. If someone needs to leave the chain, they just walk away. We don't need a new shopping cart. There's one less person now. And we just hold different hands where that person stepped away from. So anyway, just a couple of ways to visualize it. I'm also going to draw a picture of it. So each person in Hands Across America, or each link in a chain, we would refer to as a node in computer science. I usually draw pictures of nodes like this. The box represents the data to be stored. Let's just say for now that this is me in Hands Across America. And the arrow represents the link to the next box or the next person or the next link in the chain. And the way you build a linked list is you just add more nodes. Tony, you get on there. Hopefully that's okay. You're on. Oh, shoot. I made you a smaller node. That doesn't seem right at all. There. And actually now you're kind of a fancier node than me for there. And then to add another person, which I'll try to make the... and we just keep adding nodes to build the list. So what's weird about these structures is that in some ways there is no list. In some ways, a singly linked list is really just one of the nodes that we think of as being the list and the other nodes that it is chained together with, which is just kind of a strange concept. You'll see it in code and you'll get used to it being that way. So once we have chained together one or more nodes, we start to get a linked list. And if we want to take one of the nodes off the list, then we simply just deallocate the memory for that node. So we never have more memory being used than there are nodes that are storing data. And if we were to all, by the way, leave the list, we'd end up with an empty list, which would be a list that currently has no nodes in it. So the node is the building block. And the box represents whatever data we put in it. Now what's funny is that this arrow is a pointer in C++. And it's a pointer to one of these things, which is going to look weird because a node is data and a pointer to a node, which is kind of weird. It seems a little bit wrapped around on itself. So a node is data and a pointer to another node. Here's a node, which is data, and a pointer to another node. Let's go build it in software so we can see what it looks like. Make sure you can see. Give myself a new REPL. Week 10. That is good. So what would that look like? Let me make sure you can see. I'm glad there's some people here on the live stream because you'll catch me if I forget to change the view. Okay, so my node, which was the box with the arrow, what does that look like in code? I could use a class or a struct for that because we're talking about two things. Let's use a struct, and we'll call it a node. So this is how we would model that concept in code. Let's say that our box is going to hold integers for now. So we have an integer, which is the data part, and then we have a pointer to a node, which points to the next node in the chain. Kind of freaky looking at first. So this is what that box with an arrow looks like in software. We have the box part, which is whatever the data is. And then we have the link part, which in C++ is a pointer, and we will call it next. Let's go back to the picture and label one of these things up. So here's the data. Here is what we're calling next, which is the way that we connect one to the next node. This one also has data in it. And then next. Next, not you. All right, so there's that struct. In this case, we have two of them. So let's go build one real quick. I'm going to put just 10 in one of them, and then I'm going to connect it to another one that has 20 in it. And then you're going to see the last thing I will do is the last link in the chain that's a singly linked list will have no neighbor, and we will use the C++ null pointer syntax to annotate or code the fact that this node has no neighbor on it. So let's go code this node with 10. Next points to another node, which will be a node with 20. And its next will point to null. So let's write that in code. All right, so here we go. Yeah, let's go ahead and just do it dynamically from the start. So how to explain this in a way that sort of keeps my flow going. The way that we do these dynamic link structures is with dynamic memory. So we are creating the individual nodes. We're allocating memory for the individual nodes as the need for them arises. So to build these structures, we do a lot of dynamic memory. And typically, every node that we use to build the structure is going to be created dynamically. So let's build one. So need a pointer for this. I will call this node N1, and I will say equals new node. So there's the first node. It is not populated with anything yet, so let's populate it. N1, which is now a pointer, so I got to be careful about that. Its data is 10. And let's go ahead and just say initially it's alone. So in my picture, I just built this N1. Its data is 10, and its next actually just hangs out to null at the moment because it doesn't have a neighbor. So now let's add another node, and then we will connect the first node to the second node. Okay, so there's the first node. Let's make the second node. This node's data is 20. and this node's next is null. Okay, so now we have the two separate nodes. They're just a little box for data and then that arrow that points at nothing to start. But we want this arrow to point at N2. So we're going to say N1 next is N2. Now this is new and novel in terms of reading and understanding the syntax. The way I read this, since next is a pointer, what I'm really saying when I assign a value to something that is a pointer, I know N1's a pointer also, but N1 next is itself a pointer. So when I assign a value to a pointer, the way I read that is N1's next pointer points at. That's how I read that. So what does N1 next point at? It points at N2, which in the picture looks like this. So N1, this is N1. This is N2. So N1's next points at N2. N2's next still points at null because it has no neighbor. Freaky stuff. So let me redraw that. It's easier to flip the page if I pull the pad. Oh wait, why don't I just rip it? Oh, because I might want it. All right, so let me redraw it and let's add another to the chain. So we have, here's N1, has 10, has a next. Here's N2, which has a 20, and the next. So let's build an N3 with a 30 and then connect these up. So the big question coming up here is how do I connect chain together N2 with N3? I'll do this part though. So these are all dynamic structures, which means every node is allocated dynamically. We will put some data in there. 30. We will point its chain off to nothing. So now the big question is, how do I connect those things up? How do I get N2 chained into N3 so that I have this nice sort of chain of N1 to N2 to N3? What did I do? I erased something. There we go. Okay, so how do we chain those things together? It's a hard one. Nice one, Tony. That's exactly right. So N2 has that linker, and I want it to link up to that new node that I just made, N3, and now I have built the chain that I want. That code, good one, Tony, gives us, I'll just scrub that out and say, go here. Conceptually, it doesn't really matter where we draw the boxes as long as the arrows connect to the correct things. This arrow, I know you can't read that, but that's null pointer. Okay, so now we have that all chained up. And we can keep going, of course. Let's Yeah, that's probably enough. I could also, if I wanted to, just to point this out to you, so I could have an integer node, and I could also, if I wanted to, have a string node. And the point here is just to draw your attention to the fact that I can have the nodes contain whatever I want. Now, to build a chain of them, though, notice that to chain a string node together, I need to chain it to another string node. I guess technically I could chain it to an integer node, but that would be weird. Oh, darn it. Thank you. Someone caught me in chat. So what I've done is I've changed the name of the node to be int node, and then I've changed the linkage to be integer node. Change the linkage to be to another integer node. And this is how this pretty much always works. You rarely create, I can't even imagine a situation where this makes a whole lot of sense, but you chain nodes containing the same kind of data together. It would be weird to create a collection of a whole bunch of different kinds of data, and it would be kind of difficult to model that in software. Anyway, it's not impossible, but it'd be difficult. So anyway, the point here is you can change what you put in the box by creating by using different data types for the data that goes in the box that the struct represents. But we tend to create lists of nodes that contain the same kind of data in their boxes, which is how we're always going to do it in this class. But just to point out to you, it doesn't have to be an integer. It could be a string. It could actually be some other kind of struct if you wanted. This thing right here can be whatever you want it to be that goes in the box. Then we're careful to make sure that we are chaining nodes that are storing the same kinds of data together with each other. So I'm going to leave that there, and I'm going to put this one back so that I don't break the code I've already written. Okay, so that's how the most simple kind of node works. Nodes don't actually, in our class, get a lot more complicated than that. If you go on and do a PNA3 class, you will see nodes that get more complicated. Ours get a little more complicated, but not a lot more complicated. Okay, so we've talked plenty about nodes. I'll switch the view again. We've talked plenty about nodes and how we represent the data and the linkage inside of a struct, and then how we actually sort of dynamically create each node with new, how we use pointer syntax to get the data, to get this link, and then how we link one node's next to another node, one node's next to another node. And then the last node in a singly linked list always points at nothing. It's the one at the very end of the line. This is always true of a singly linked list, by the way. The links go in one direction and eventually dead end at a null pointer. We can actually code around this fact, by the way, interestingly. Switch back, and we can actually use these linkages to iterate over a collection of nodes. So I'm going to do that right now. And in fact, no, maybe it's less confusing. So let's make a node temp and start it at n1. Hopefully I switched the view. I did. So now let me switch and draw a picture of what I just did on line 32. So what I just did is this. So it also takes some getting used to, but there's not actually any limit to the number of pointers you can make to point at stuff. So technically, at this moment, temp points at this node, and N1 also points at this node, even though we actually sort of think of this node as being the N1 node. We actually used a pointer to generate it. So N1 is actually pointing at this dynamically generated node. And since temp points to where N1 points to, temp is pointing at this same node. It takes a while to get used to this. So here we have on line 32, temp points to what N1 is. That's the picture we just switched over to. So what can we use that for? Well, we can say while N1 is not the null pointer, we will, temp, let's use temp, is not the null pointer. We will print out temp's data and follow it up with the space, and then all of that stuff with an end line. Okay, so first step is to print temp data, which at this moment is 10. Then we can walk temp over. So we can say take temp and now point it to whatever is coming next after temp. Pretty freaky. So let's see what that looks like on paper. So here's temp, print out its data, and then we say move temp to point to wherever this next points to, which is this one. N2 never even came up. We didn't even refer to N2. We simply used this next link to move temp over to the next one. So now in the while loop, we check, did temp become null? It did not. It's sitting on 20. So we'll print out the 20 and the space, and then we'll move temp over again. Back to the paper. So we print out the 20, and then we move temp over again. So temp is wherever temp next goes, which is this one now. So we'll print out the 30, and then we'll say temp moves to wherever this one points to, which is null pointer, which breaks the loop. So we should see 10 space, 20 space, 30 space, and then the loop breaks because temp finally walked off to the last link that was at null. So let's run, it should say 10, 20, 30. So there's the 10, 20, 30, which is darn cool, and it's even cooler still when you start to understand how all of this could possibly work. Then it becomes pretty neat. Okay, so that's null stuff. Now let's talk about so I've talked about lists. I've talked about nodes, and I mentioned the term linked list. But I didn't really talk about, I haven't written any code that looks like anything that's called a linked list. So where does this thing come in terms of code? Where does the singly linked list come in terms of code? We don't need the singly linked list to create nodes. And we don't really need the singly linked list. Like there's not even anything in my code that says or looks like anything that's called the singly linked list. There's just nodes. So what is this singly linked list? Singly linked list. It will be a manager of nodes. So it makes our lives a lot easier if instead of trying to manage a whole bunch of nodes all over the place, and we create them and we chain them together, and we step through them with those temp pointers to print out their contents. It turns out that life is a lot easier if we create code to manage a collection of nodes. So the nodes still are kind of what's most important, because the nodes contain the data and the nodes contain the connections that is the list. But it is very helpful if we have code that helps us in the task of managing nodes. Think, for example, CRUD operations on nodes. Creating nodes, reading nodes, updating nodes, deleting nodes. It's helpful to have code written to do those operations for a grouping of nodes as opposed to the individual nodes having to figure out how to do that themselves. So we'll use this manager to do CRUD operations and then also to manage metadata. And I'll put a sort of a sub list of what I mean by that. So we're going to create some code, call it a single linked list. It doesn't make the nodes go away. It simply gives us a place to organize programming that will manage a collection of nodes, which mostly is CRUD operations. Create a node and chain it. Read a node, access them. Update them, access them, and then overwrite data fields. Delete them, remove them from the list. That will be one thing that this single linked list does as a manager of nodes. It will also manage metadata on the list. So what I mean by metadata is things like the total number of nodes. So no single node can keep count of how many nodes are present because each individual node only knows about its own data and its connection to the next node down. So the singly linked list manager can be used to keep track of metadata such as how many total nodes are here right now. We can use the singly linked list to stringify our nodes. In other words, to give us a nice, pretty string containing all of the data from the nodes. The nodes themselves can only print their own single piece of data, but the singly linked list as a manager set of code can actually cycle through all of the nodes and build up a string with the contents of all of them. So that's another kind of the metadata can include sort of emptiness, meaning am I even managing any nodes at the moment or not? Kind of like string empty. We can actually, in our manager code, give ourselves the ability to check and see if we even have any nodes available. That is, of course, related to the total number of nodes. If there are no nodes, then we have an empty list, but it is convenient and it is a common kind of function. Thank you, Isnam, for bringing that up for the earlier example, that people want to just have a function call that says, is it empty? So for a manager of nodes, emptiness would mean there are none here. And then finally, what's the word I'm looking for this? I had it in my head just a second ago, and then when I went to write it, it left my head. Oh well, I'll call it a marker, and then I'll come up with the fancy. So the manager is not nodes. The manager is just giving us the ability to kind of work with a collection of nodes. Sentinel is the fancy word for what I'm saying. So the singly linked list can also give us the ability to keep markers on the collection, to keep track of things like who's the first node or possibly who's the last node. So what I mean by a sentinel is a special piece of code that marks a node that is the first node in a list, in a singly linked list. We can also use sentinels to do things like keep track of who's the last node in the list, which we won't do initially, but eventually we will add that functionality. So these are, in my opinion, metadata. To manage a set of nodes, we have to be able to find at least one of them, which would be the first one in the chain. If not others who have special properties, like the last node in a chain is different from all the others because it has no neighbor. The first node in a chain, if we were keeping a marker or sentinel on it, the first node in a chain has no neighbor to the other side because it's the first one. So we're going to write some code for this. And I'm building it from scratch during the live stream just so you can see me build it from scratch. So let's switch back and create ourselves a singly linked list. I am going to comment out this whole main for now and get it the heck out of the way. Okay, so let's create, I'm going to use a class. So I like structs for kind of data only situations, and I like classes for data and functions situations. So let's make a class to be a singly linked list. And this is just one of those hard and weird concepts. This is not nodes. It's a manager of nodes. This is what the node is. This is not nodes. I mean, it is kind of, you will find nodes using it, but there's the node, which is this thing, and there's the manager of a collection of nodes, which is this thing. We don't have this concept from arrays or vectors. In our minds, most of us anyway, an array is the data inside because the array means all of it. And in our minds, a vector is the things inside because the vector means all of it. A singly linked list does not in the same way mean all of it. A singly linked list just gives us a way to do management operations on a series of nodes. All right, so there'll be a public section, there will be a private section. Let's do the metadata first. So in code, let's say num nodes this way. So simply an integer to keep a counter on the number of nodes that are present. The metadata for the sentinel is going to look funny at first, unfortunately. But the sentinel for the first node in a list, most people in computer science will call that the head node. It's the head of the list, and there is only one head of the list, and it happens to be a node. Okay, and let us make a constructor here. I'm going to do it in place to keep the code a little bit simpler to look at. So what would we want of our metadata when we initialize a singly linked list? Well, we're going to have no nodes, and our sentinel will have no node that it can refer to at first. And if we had a main here, then we would have a singly linked list, which I will call SLL. Remembering to try to force ourselves to think of this not as the nodes, but rather as something that manages nodes. Okay, so what does that look like in paper? So somewhere down here will be all the nodes. And then we have up here the singly linked list. And it has two pieces of metadata. There's no nodes. We're kind of conceptually saying that this would be the nodes that are being managed. And then we also have this head, which initially points to nothing because there's no nodes. So there's our singly linked list. It's also going to be kind of weird feeling at first that the list itself is not dynamic. It doesn't need to be. It's not the data. The nodes are the data. They will be dynamic. The manager of the nodes does not need to be dynamic. Kind of weird, huh? Okay, so now let's give it some functionality. Its most important bit of functionality is that it has the ability to, I'll be explicit. It's a most important bit of functionality is that you can use the singly linked list to manage the problem of creating and adding nodes to a collection. So what does the singly linked list need to know before it can actually create and add a node? It needs to know what the data is. If the singly linked list knows what the data is, it can create a node to hold that data. So let's do that. The data is simply going to be an integer. Why? Because the nodes that we intend to manage contain integers for their data. Okay, so now what does the linked list do with this data? Well, it needs to create a node. So notice that the linked list is kind of where we're going to manage the problem of dynamic node allocation. So we're going to create a new node. We will populate its data with the data that is our parameter. We will make sure that to start, it has no neighbor. So I'm going to go draw a picture of this now. This is all the singly linked list doing this. Okay, so here's what the singly linked list just did. It created a node, called it in. It put the data inside of it. And it pointed this thing at null pointer. So the singly linked list actually just did this job. The problem we have at the moment is that we haven't updated the metadata. We haven't updated the number of nodes to account for the fact that we just built one. And we also haven't updated the metadata, this sentinel, to keep track of this node. Notice here, by the way, that when the head is null and we create a node, that's the first one. Yeah, so Edcast asked, is this like a node constructor? It is. More or less the singly linked list is handling the problem of constructing the node. Although we can have the node do part of that work for itself, which we'll add in just a moment. Okay, so we need to update the metadata. So we need to update the metadata, and then we need to say head, let's say this. Keep track of this is singly linked list stuff now that we are keeping track of. So we'll update the metadata. So the list's num nodes goes up by 1, and the list's head sentinel shifts over to mark that new node. So let's go draw a picture of it. So we bumped this up. And we move this now to point here. Pretty crazy. Okay, so now let's go use it. And I got to remember to let you see when I use. So here we go. Let's go down into main and create and add a node on the list. So we'll do that. And we should get the picture that we imagined. So now let's see what our algorithm does if we try to make another one. Okay, so if we try to make another one, hopefully you're seeing what I see. Yep. What does the algorithm do? It makes a new node, it populates it with data, it nulls out its connection, and updates its metadata. So let's see what that looks like in the picture. Okay, so the algorithm is actually going to reuse this n. So we get another node. We populate it with data. Now n is being kind of used over here. Null this out. And then we update num nodes. And then we move this head sentinel way around over here. I'm going to do it in pencil this time because it's a problem. So hopefully everyone sees that I just orphaned this node. There's nothing that gets me back. The n has been reused. The head is moved. The counter is increased, so I know the node's there, but it's been orphaned. There's no metadata. There's no linkage to it coming from any direction. It is completely orphaned. So what do we call that when we dynamically allocate a thing that we can no longer manage or have forgotten to properly manage? Memory leak. Good one, Magenta. That is a memory leak. Nice one, Isnam, also. That is indeed a memory leak. So memory leaks can be me simply forgetting to delete things that I allocated with new, but a memory leak can also, and in fact is often more likely to be caused by losing any linkage to a dynamically allocated thing. There's nothing that links here, and I'm completely messed up at this moment. So I didn't want that to happen. What I wanted to happen was this. I wanted this one to chain onto this one, and this one to remain the head, because the first one in should remain the head. Or maybe it's simpler. I'm going to redraw this. Or we could do this instead, and let's do it this way instead. Or we can say, so we have head, we have num nodes. This is the singly linked list. Or we could do it this way instead, which would be easier, and let's do it that way. So this is the first one. That was head. So now we bring in a second one. So let's do it this way instead. So the first one was head. It's easiest, and we'll look at algorithms to do the hard way, but let's do the easy way, which is, let's make this new one. Let's put every new incoming node in the front. Okay, so what we really want is this. At the end. So the new one with its data becomes the new one, becomes the new head. So we'll move the sentinel to the new one, and then we'll chain the new one to the old one, the one that used to be in front. So we'll keep adding in the front. So we need an algorithm that does this for us. So let me just walk you through. Let's write some code for it and then see what's wrong with that. So let me switch you back. And let's do that right in here. So increasing the number of nodes is fine. Putting the head on the new one should be okay. But now what we really want is, this is going to blow your mind a little bit. That's the sentinel. And then this is the node that the sentinel is marking. That's its next link. So let me just walk you through where this can break. All right, so I have this situation. I'll just let you see me draw the picture. So I'm not going to go over 2 hours today, but I'm pretty close to the end. Okay, so here's our situation. We have this new node. We have head over here. So what we just did in our code is we said this head points to N. And then we said this head next points to what? So we have the same problem, that moving this head marker away from where it used to be cuts off any connection that we had. So somehow we have to address this problem, and I'm going to do it kind of slightly quicker, but the trick here is to make the internal connections first before you change metadata. So we want to make this connection before we change the metadata, because if we have this connection while we still have N, then everything works. So I'll just do it, and then we'll come back and I'll draw a picture of the steps. So this has to wait for a moment. So we're going to do this first. So do the metadata, which is this. Do the internal connection, sorry, first. So the internal connection is this part. Where do we want that to point? What head currently is. So let me draw a picture of just that much of the code. So what does it mean to point this head next? Point it at this head, not this head. N. N next at this head. Goodness. Okay, so here we go. Here's the new guy. So N next. I'll use pen. Now points here. So at this moment in our code, we still have N on the newly allocated node. We still have head pointing to what used to be head, and now we have chained together the new guy with the old guy. So this is what we have in code so far. And our last step then is to move this, the sentinel, over to N, which I guess I can erase, and then I'll draw in pencil again. I know a whiteboard would be easier, but not on my desktop, unfortunately. So let's do this connection last. And notice at the moment that N still kind of holds. Okay, so there's that. And then now we can say this head equals N, and now we're all in business. Kind of crazy. Now what that means, of course, is that the 20 goes in front of the 30. So let's try one more and just use the picture to see if everything's going to work out. So let's see if everything works itself out if we create yet a third node. And I'll just kind of, I know we create a node, we increment the counter, we do the internal connection on the new node first, and then we move the sentinel. All right, so here we go. Here's a new one. This is the third node. In fact, I can just put the numbers in them at this stage. So that's the new node. This is our situation. We used n to allocate the new node, so we have this. So in our algorithm, we just bumped up the node count. We do n's internal connection first. We take n's next and point it at the current head. And then we take the sentinel and we move it over to refer to the newly allocated node. And now we have this chain, which in a picture just looks terrible, but that's the chain that we have. All right, where am I at? 11:34. I'm going to try to finish in 10 minutes if I can. Okay, so let's do one more bit so you can see how I build it. So another thing that we want to be able to do is to stringify. So sort of as metadata, get a view of what all the data in the list is at any given moment by putting it in a string. Do I have SStream in here? I do not. Oh, you're seeing the paper. Sorry. Thank you. Thank goodness you guys are here. Okay, so I'm going to add to my list a stringifying function as metadata, more or less, right? I want to view the current contents of all the nodes that the list is currently managing. So I need string stream. Okay, and then here, so old stuff. Okay, so we're going to do the same kind of walking that we did on the other nodes. So we'll give ourselves Oh, thank you, Edcast. I appreciate that. I know my pictures. So Edcast and Chaz just saying that the pictures, in spite of the nasty mess I'm making, are still helpful. So thank you for that. I appreciate it. Yeah, and I'll try to, not have them go too crazy and still kind of show you what's going on. And then eventually, when I know that most of us are getting used to it, instead of drawing arrows, I can just kind of like use the end of a pen and point things and kind of hope that you kind of understand what I'm doing. Okay, so we're going to do the same process. Temp. So notice the list is going to use this sentinel whenever it needs to like go through the list to do something. So in this case, we want to walk across the list and get all the data from out of it. So we'll start where this sentinel is marking a temp. So here's what I mean by pointing a pen, by the way, real quick. So let's say this is temp. I'm going to start it here, and then I'm going to march it across until it hits a null. But I'm going to start where this metadata piece, right, this sentinel, tells me that's the first one, and then I will go next, next, next until I hit null. So while temp is not null, we will get the data, put a space in there, and then we will move temp over. Walking with pointers, which is just a really cool thing. At first, at least for me, if you get this right off the bat, then I'm envious of you, because it took me a long time to feel comfortable with the pointers in this fashion. It's just very hard to look at temp arrow data and make sense of what that is. But temp arrow data is basically pointing at a node and saying, what's your data? Temp arrow next is pointing at a node and saying, what's your link? But then this kind of weird, I can take temp and shift it over to the thing that it's currently nexting to, right? Just kind of weird. All right, so space, space, space. Let's try it. And notice it's in reverse because we were putting every new one on the front, because that's what we're doing in lab this week. That's the easiest one to do, is just take the new one, make a node for it, stick it on the front, and now make the new one the front. And then the other kind of metadata that we have here is we can get the size just with the num nodes. And we also have the ability to allow for an empty call, simply because it's very common function in data structures. So they could easily check size equals 0 for themselves. This is just a convenience. So Magenta asks in chat, why is building backwards better? So building backwards isn't better, it's easier in code. We will, though, in the coming weeks, write the code to attach data to the end. So the reason why we're putting data on the front now is because this is the easiest algorithm on a singly linked list for adding a new node. To add a node at the end, we'd actually have to iterate and find a pointer that's pointing at nothing and then connect directly to that iterator. So it takes more work and the algorithm is more complicated. So we're putting it off to give ourselves kind of the slow build up to those more complicated algorithms. Anyway, hopefully that makes sense. We're doing it this way because it's the easiest one to do. Okay, so there are those things. I will share this. This is a public repo. Now we're going to go look at the lab. So we can look at the differences in the lab, even though I've just given you some of the critical algorithms. So let's look at the lab and see how it compares. I will share a link on the lecture page to this REPL that I just did. All right, let's go look at the lab. Did I switch back? I did, thank goodness. Okay, so we have a unit test is lab10.cpp. It's a very short one. We have slist.h. This is the API, so let's look at it. So notice just the differences. They're not significant. So slist, instead of spelling out singly linked list, which you'll be grateful for, I'm sure. Good question. So Magenta in chat says, some mental gymnastics for now, but simpler code, I think. Yes. Yeah, so we're hoping that, my hope is to limit the amount of exposure to the crazy stuff while your head begins to wrap around dynamic memory and pointers and nodes and linking them. So we will slowly kind of add in over time the more complicated algorithms that require moving back and forth in the list when we can do that. Taking nodes off of a list can be difficult and is fraught with errors. So yeah, we'll be adding in the algorithms over time as hopefully we get more and more familiar with the look and the feel of it. Okay, so push front is the common terminology for create and add a node that we just did. So this is the create and add node algorithm that we just did. Front. let me do a front. I'll switch over to my REPL and add a front. So the front code, so this one, but create and add node is push front. Front, what's it supposed to return? The data? Returns the value, the data. Oh, also, by the way, I'm using the term value in here to refer to the data. Okay, so the data here is an int front. It throws an exception. So the exception here, which I'm about to break my code. Is it called accept? What's it called? Standard accept. Sorry, I'm switching around too, but I want to get you off of here quick. Standard accept. So the front one, what's going on here? Well, part of the manager's job, the single linked list job, is to allow accesses to the data for CRUD operations. But I can't return the data from the first node in the list if there is no first node. So what we do then is we check the head sentinel. That's naughty, right? I think it was logic error. Yeah, empty list. So adding a node doesn't need to worry about null stuff, but retrieving the data that's the front, the data from the first node in the list, that's potentially a problem because there may be no nodes, so we need to handle that. Else we can use the sentinel to get to the node, and then once we're at the node, we can return the data, which I know that sort of chain of pointers is kind of weird. Although if you go back and look at the picture, well, this is just referring to the list itself. So my sentinel that I call head points at what data? That's front. What else can I help you with? Get size, I just called it size. Empty, we just did. To string, uses commas instead of spaces. And then the tricky bit is, how do I keep the comma from going on the last element? Should I show you? This will be my last act on the live stream. So I will let you in chat tell me, do you want me to show you how to avoid the comma at the end, or do you want me to leave it to you to figure out? Okay, so magenta votes a yes. How do we keep the last thing off? Okay, edcast seconds. So in the toString, so notice here we are putting a space after every one, but not everyone wants a space. Only certain ones want. And it turns out that the ones that should have the comma or the space are the ones that have a neighbor. So in other words, next, I check to see if there's a neighbor by checking for a not null. So this check right here means, oh, it's not null, which means that there is a neighbor. If I have a neighbor, I'll put a dash just for fun. If I have a neighbor, then I want a separator between me and them. So that's the whole trick of getting the comma off, is check the next one over to see if there is a next one over. And if there is, then I need a separator. Kind of cool. And then lastly, this little weird bit here, which I'll go ahead and do in my sample. So I've actually embedded the struct definition inside of the class. I have added a constructor inside of the struct itself. And I have also declared a pointer to one of those structs all the way inside. So here's what that looks like in my REPL, and then I can be done. So right now I have the struct outside. It turns out that I can declare the struct. Well, I can do this for one thing. It's very handy to have a constructor in here. So that I never forget the proper setup for a node itself. So I put a constructor in there. But the other thing I did is I took the whole struct. I'm going to cut it. Took the whole struct and I actually embedded it inside of the class, which you are allowed to do. So now the singly linked list is managing a node that it defined itself, as it were. So here's the struct definition inside of the class. And it turns out that if I have the definition handy, well, I don't need to declare the separate node star head here. I can simply say, yeah, one of them. So one of these guys, I want a pointer to it called head. This is just, to me, it's a little scary looking at first, but I also like the cleanliness of it. So now I don't have a struct definition out in space. I only have a struct definition in the context of the place that needs to have it, which is the singly linked list itself. And then I took advantage of the fact that if the definition of the struct is right here, I can just simply, right on the tail end of the definition of it, declare a pointer to one. So that's what that part is. And now this will all be shared in the readings and lecture, which spoils a lot of your fun for this lab. But you do have to bring it over and then match the words together. So at least you do have to be thoughtful about it. Okay, I need to stop. The REPL from today, the linked list one will be shared. The project one will not. That's entirely stream/video stuff, but I left it on the screen for a long time and spent a long time talking about it. What else? I think that's it. So project 2, which I know is not linked list stuff. So we're kind of looking ahead with the linked list while we're finishing the project 2. But anyway, Canvas Inbox, office hours, Piazza. On Piazza, a good rule of thumb, as I've said before, is kind of one function worth at a time per question or discussion, so that we don't end up just kind of all in one place doing a huge, giving the lab away to everybody without at least asking them to be thoughtful about it. Okay, so have a great week. Get in touch if you need anything on the second project or on this lab, and otherwise I will see you on Monday morning next week. So take care in the meantime.